The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone. Thanks for coming to our webinar. We're going to give everybody about 1 more minute, then we're going to get going. We have a lot of content to cover today, so don't want to spend too much time waiting around. So about 45 seconds, we're going to get started. Hello, everyone. Welcome to our webinar. Thank you very much for joining us today. I'd like to welcome everyone. Today's webinar will feature presentations from QLab Corporation and Thermotron, so we're really excited to be working with them to present some great information today. Just a few housekeeping things before we get going. We will be sharing slides and recordings after the webinar today. We'll email you a link in the next couple of days, by the end of the week, with links to be able to download the presentations. If you have a question during the presentation, you can use the questions feature of GoToWebinar. Go ahead and type your question in there. We'll have time during the presentations today to answer those questions. And we have QLab and Thermotron people here in the kind of webinar who are here to answer questions as they come up. So we should be able to address those as we go with some of our staff. So thank you to the QLab and the Thermotron folks who are joining us to help out today. Again, we have a lot to cover, so I'm just going to throw it right over to Bill Tobin at QLab to get us going. So, Bill?
Thank you for the introduction, Mike. As mentioned, my name is Bill Tobin. I'm the Senior Technical Marketing Specialist here at QLab. And today we're going to be talking about laboratory corrosion testing. Just as a primer ahead of time, when we talk about corrosion testing in this, we're primarily talking about atmospheric corrosion, which is going to be different mechanisms than chemical corrosion or underground corrosion with like pipelines or something like that. So the topics that we're going to cover are, we're going to go over the various types of accelerated tests that people can perform. And then we'll kind of go through the history of the development of accelerated corrosion testing, starting with continuous salt spray, then moving on to wet, dry, cyclic tests, and then the first and modern generations of corrosion test methods. So the first thing we wanted to cover was to go over the different types of accelerated tests that exist, because it's important to identify what you're trying to run, because that will help you pick the appropriate test for your application. So the first one that we're going to start with is talking about quality control. These tests are designed to be very fast, and really what you're trying to do is find some sort of catastrophic failure in the material that you're running. It's not really necessarily used for development of new formulas, but it is used in certification that a supplier is giving you an appropriate material. Some research, you can do this as a quick test to compare a known formula to an unknown formula. The next step of test is what is called a qualification. This is still a pass-fail test, but usually it has more development associated with it. Like an OEM or maybe an industry group has come up with a set of standards that you need to meet. But it's similar to a quality control test because you're not actually comparing things to outdoors. But what this does give you is an opening to development, because If you know that this is the minimum requirement to meet something, that can be used in the development of new formulas. Now we have this large bold line that separates the next one, and the reason for that is that quality control and qualification don't require any kind of real-world data. But the next step, which is correlative testing, really does need to have real-world data to ensure that your test is giving you an accurate representation of what your material is going to see. And this is a lot better for the development of materials because you can get rank order data. You can test many different formulas next to each other and identify which ones might be better performers so that you can make an educated decision on what you want to sell into the market. But in order to know that the accelerated test is actually giving you realistic results, that the best performer in your accelerated test is also going to be the best performer outside, you need to have natural exposure data. Now, this can be run at benchmark sites, for corrosion testing. Florida is often used, or a shoreline marine site can be used. But this could also be data that you've gathered from customer returns and if you have an idea of how your product lasts outdoors. What you're really looking for in these tests is you want to make sure that the results outdoors, the failure modes and mechanisms, match what you're seeing in the accelerated test. And then the last one is predictive testing. Usually when someone's new to accelerated testing, this is really what they're looking for, which is they want to know if I run this test for 1,000 hours, that's going to translate to X amount of years outdoors. And the problem with this test is that it's very formula specific, and small changes to a formulation can have a big change on this. This is great data to have, but it takes a lot of time. You need to know how a number of different similar formulas operate outdoors. You need to test a lot of different formulas in different accelerated tests. It's long and open-ended, but it's very valuable for companies that are trying to identify warranty contracts. We will get the question, how many hours translates to a year outdoors, and there's no good answer for that, and it's going to vary based on different test method and application use. So we don't have the answer here, and that's ultimately good for you people who are going to be doing accelerated testing, because if you are able to establish that, that's a huge competitive advantage that you might have. All right, with all that said, let's get into the actual accelerated corrosion tests that exist. So the first one we're going to talk about, which was the first one developed, is what's called continuous salt spray testing. It's very simple. You have a fog nozzle that's atomizing a salt solution into the air, and the specimens are exposed to this condition continuously for the duration of the test. The most common form of this is known as ASTM B117. And it's important to note that ASTM B117 is actually over 100 years old now. Still used widely, still probably the most run corrosion test in the world. The method was first introduced in 1914, and it was first published in 1939. Now, part of the delay between those two is they were working on trying to establish what salt solution they wanted to use. They ultimately settled on a 5% salt solution, but there was some talk about using a 20% salt solution prior to that. In 1964, the U.S. adopted it as a national standard, and then even today, it's still the most used test method for quality control of high quality coatings and metallic conversion coatings. So to give a little bit more detail, as I mentioned, this is a 5% sodium chloride solution, and the test is run at 35 degrees Celsius. The pH of the solution is supposed to be neutral. If it's acidified, it's going to cause a higher rate of corrosion. And it's important that the mist is finely sprayed and that it's not actually washing off specimens. What's great about this test is it's got very good repeatability and reproducibility, and there's a lot of testers on the market that are available to run this test. And even tester to tester, you're going to get similar results because a salt fog is pretty easy to repeat. Now, there are some modifications of the salt fog. As I mentioned, making it an acidic solution is going to increase the rate of corrosion, and there are some tests that use that. What they generally use is an acetic acid to drop the pH down to about 3, causing a highly acidified solution. There's also the CAS test, which adds copper sulfate to it, and that stands for copper accelerated acetic acid salt spray. And CAS is a very, very volatile test. And so the idea is you really only run this test on very high durability inorganic coating systems, or say like an anodized aluminum, things that are going to last a very long time outdoors, and things that will last a very long time in just the neutral salt spray. That's usually when CAS is used. Now, the biggest limitation of salt spray is a lot of the failure modes you'll get in salt spray are not realistic. They're not the same thing that's seen in outdoor environments. It's not the same thing that's seen in like some of the more modern corrosion test methods. And so it's not really a great indicator of how something's going to perform outdoors. It's still very useful to make sure that, it was applied properly. You're looking for catastrophic failures as a quality control test. And also it can be used as a qualification test, comparing it to materials that work outdoors. So again, what we would classify this as is a quality control test foremost of anything. So to further development, they were happy with the quality control test, but what they were really looking for was something that had better correlation to the outdoor mechanisms of corrosion. And so in searching for that, what they said is, things aren't exposed to salt fog all the time. So there's many times where they're going to be dry as opposed to being in that salt environment, even in a marine condition. And so they started cyclic tests, which are alternating between salt fog and drying off of the specimens. The main one that's known is ASTM G85, which is also called the Corrosion test, based on the creation of the test. Corrosion stands for protection is adhesion, which is a little confusing, but if someone says Corrosion, this is the test method that they're talking about. It uses a very dilute solution of sodium chloride. I believe it's 0.05%. And it uses a dilute solution of ammonium sulfate as well, of 0.35%. And just recently, the American Architectural Manufacturers Association, AMA, replaced B117 with this test for testing superior coatings on aluminum. So it is, even today, it's just recently been adopted as kind of the main test method. There was a test that was done to simulate the outdoor exposures. So what they wanted to do is the SSPC, or the Society for Protective Coatings, at the time it was the Steel Structures Painting Council, they tested 15 different systems outdoors for 31 months and also compared various accelerated tests, including B117, Corrosion, and some of the cyclic tests that we'll be talking about in a little bit. And they wanted to see what had best rank order correlation outdoors. So the two test methods that we talked about just recently, as you can see, their rank order correlation is negative 0.11 and negative 0.07. If you're unfamiliar with Spearman rank coefficients, a 1.0 means perfect correlation. That means that the best performing material performed the best in both tests, the worst performing material performed the worst in both tests, and every other material fell in the same order. A negative one would be a complete reversal. The best performer in one test would be the worst performer in the other test, and so on. And so what this shows us is that when comparing outdoor results to these test methods, it was effectively random. These did not give any kind of good correlation and could not be used to identify whether a material is going to perform well outdoors or not. But there were some other tests that they were performing. One of them was combining corrosion and weathering together. This was developed in the 1980s by Sherwin-Williams, and there's a couple versions of this exist in ASTM and ISO. But the general running of this is that you spend time in a corrosion chamber and you spend time in a fluorescent UV chamber, and in ISO they also add in 1 day of freezing, and the idea is it simulates real world exposures because things that are outdoors are going to see that UV and they're also going to see that salt. And the idea is that the coating is really what's protecting it from the corrosion, and the UV is going to degrade the coating, which makes the metal more exposed to corrosion. This particular test, what they used, the Prohesion test method, which is 1 week, this is the ASTM version, and it used 1 week of Prohesion, which is 1 hour of salt fog and 1 hour of dry, and then it used 1 week of ASTM G155, which was 4 hours of UV exposure and 4 hours of condensation. And so here are a couple of samples that were pulled out of it. And so when looking at this, the top shows the performance in the accelerated testers, and the bottom shows the outdoor exposure. And as you can see, even though the results aren't exactly the same, latex was the best performer, the alkyd was a little bit worse, and the epoxy was bad and also had this blistering that didn't appear in the other two. And both tests showed this. And what they came out with that is this combined corrosion test cycle ended up having a rank order of about 0.7, which is pretty good for corrosion testing and weathering. So this is really what they wanted to use in order to identify how something's going to perform outdoors. Now, there were some downfalls of this test method, particularly the Prohesion test method. But the first one is that, the repeatability and reproducibility is not great. And because this was a manual test moving between two testers, the speed of the lab technician moving specimens also had an impact on the results. Do you have a slow technician or do you have a fast technician? It's going to give you different results. The other problem is that the rate of dry off during the dry period has a large impact on the corrosion rate. And if you have a tester that dries off in 10 minutes versus a tester that dries off in 30 minutes, they're going to have very different results. And they did have some poor correlation in cases with highly durable coatings. And so, these tests are still used because they're easy to run. Prohesion is very available, and but again, they're not really the best for correlation. They can be used for quality control, and they can also be used for qualification in some cases. But they really needed to find something better for replicating outdoor testing in a repeatable fashion. And that leads us to our first generation of tests. So to go one step further, what they said is things outdoors are not necessarily exposed to just salt and dry. A lot of times the air becomes humid. You might have rain conditions that don't necessarily have salt, but do cause some wetting to happen on the panels. And they wanted to simulate that. The most notable one that we're going to be talking about is General Motors 9540P. So this is an automotive test. So they chose to use sodium chloride and calcium chloride because that's a common salt used in road salts. And they wanted the solution to be applied directly because it is going to be washing away. If you're splashing the salt solution off the road onto your car, that's going to wash materials away, and it's also going to apply salt a lot faster than a fog. The salt would be applied in ambient conditions in order to try and control that step of the method. And the big one is that they used corrosion coupons to minimize test variability. Corrosion coupons are effectively, and we'll talk a little bit about this later, but they're untreated, unpainted steel or zinc that when exposed to corrosion environments, they're going to corrode, and they're going to corrode quickly. The idea with this test is that over a period of time, those coupons had to corrode within a window in order the test to be considered run properly. And the way that you evaluate it in this test is you weighed the coupons before the test, you expose them in the conditions, and then you remove the coupons, removed all the corrosion products off of it, and weighed them again. And what you were really looking is to make sure that your mass loss was in the appropriate range. There were some other options that were out there. PV1210 did a combination of the three environmental stresses that we said, but it was really designed about going between three chambers, going from a salt fog chamber to a humid cabinet to some sort of dry air room. And then the other one that was used was JASO, which is the Japanese Automotive Standards Organization. Their M609 and 610, which are called the CCT tests. where they use the 5% salt solution, but in order to minimize variability of that dry off period of time, they required a very fast transition, so that the idea is that any chambers that can meet it would all be approximately the same speed, and the corrosion rates would be closer. And again, to give you timeline, these test methods were published late 80s, early 90s. So this is just 28 years ago. Here's an example of what the PV1210 cyclic corrosion test looks like when run in a chamber. So you can see the first step is effectively, it's a fog step running at 35C, then immediately moves into a high humidity step at 40C, and then it drops down to like an ambient drying phase. So the limitations of these are they still had repeatability and reproducibility issues. Depending on what metals they were testing or what products they were testing, some would have good correlation and some would have very bad correlation. And they weren't really sure what was going on, but with some further education on corrosion, I think that the industry has started to crack the key here. So when we talk about the different corrosion rates, what's important for us to talk about is the idea of galvanic corrosion and the influence of relative humidity on that corrosion. So when we say galvanic corrosion, what we're talking about is corrosion that occurs between two different metals. So in that case, in this galvanic series, one metal will become the anode and one will be the cathode. And the idea is that when these two metals are touching, most of the corrosion is going to be localized into the anodic metal, and the cathodic metal is going to be pretty much untouched. And the most common one that we see day to day is stainless steel and aluminum, because in the real world, these two things are very often paired together. Here's a couple of examples showing what happens when you have, say, a steel spike attached to an aluminum bar or a guard railing, and where the corrosion is localized. As you can see, the spike itself is not corroded, but the metal around it has corroded greatly, and this is because of galvanic corrosion. So what we really want to do, and the reason why relative humidity is important, is that galvanic corrosion only happens at a certain point where you have full salt coverage over a material. And as RH changes, if you start to have a localized corrosion, you're going to have a different method of corrosion. If you don't have full coverage, if you don't have that electrical connection through a salt solution, you won't get that galvanic corrosion. Instead, all of the metal parts will corrode. And so the term that is used in these test methods is deliquescence. This is the idea that for salts, there's a certain relative humidity, in which case there's enough water vapor in the air for the salts to absorb that water vapor and become liquid. So if you were to put table salt on a table in a very humid room, it would become liquid even though there's no condensation forming. And that's the act of deliquescence. And the point at which deliquescence occurs varies based on temperature and also which salts is being used. So this is a chart showing the common deliquescence points at 25 degrees C for some salts that are used in salt testing. The ones that we have bolded here are the ones that are most commonly used. Sodium chloride, which has a deliquescence point of 76%, and calcium chloride, which has 31%. So let's give a visual representation of what that means. So let's say that this is a regular day outdoors where you see, time of wetness for a material. So what we're seeing here is with no salt applied, materials are wet for, about 6 to 12 hours a day. I think we've got about 8 hours here, and that's just from condensation. But if we start introducing salts, the amount of time that the relative humidity is high enough to pass the deliquescence point for potassium chloride, now we're looking at more like 10, 12 hours. When we go to sodium chloride, now we're looking at maybe more like 16 hours. And then we go all the way to calcium chloride, which had a deliquescence point of 31%. Again, meaning that the relative humidity is higher than 31%. It's wet almost all of the time. So when we're looking at this, kind of the key range for corrosion testing is that 50% to 76%, and this is, of course, for sodium chloride testing. Because at that point in time, because there is no film, you haven't really hit that deliquescence point to where the salt is liquefying over the whole form of it. You don't have that electrolytic connection. And so you're going to see corrosion of both steel and aluminum in this case. And then once you pass that deliquescence point where you start to get that full film, what happens then is you now have the galvanic couple, and only the aluminum would corrode in this case. And so how can we handle this transition to make sure that we have repeatability? Because this is where the problems with repeatability and reproducibility was happening. If a test that's transitioning spends more time in the 50 to 76 range than another test, it's going to have a different corrosion. So what they've decided to do is, there's two options here. You can do a linear transition, and the idea of that is that you're controlling temperature and relative humidity at every step, and you set how much time it's going to take to go between, say, a humid condition to a dry condition. Or you can use a less than method, kind of like the JASO M609 test, where the idea is to get there as quickly as possible and try and minimize the amount of time that it's in that transition region. So here's just kind of a visual representation of what this looks like. So this would be a linear transition over 3 hours with a slight change in the temperature and a change in the relative humidity. But the idea is this would be highly repeatable. Here's what the less than ramp is. At this point in time, it's 40 minutes, so it's a lot shorter. But the problem is that ambient conditions of the lab can impact this transition time. So even within the same lab, a test run in the winter and a test run in, say, the spring or summer can have vastly different results. So let's put it all together. Let's compare two testers that are transitioning, one slowly and one quickly, and see what kind of corrosion occurs. So for the first about hour and a half, there's no corrosion on the slow ramp, and there's about first 30 minutes, there's no corrosion on the fast one. At that point in time, these materials have exceeded that 50% where they're going to start to see the localized corrosion of both aluminum and steel in this case. And that lasts until about 76%. Now, the amount of time that each of these testers spends in that region is different. The tester that's ramping very quickly is only there for a half hour, whereas the tester that's ramping slowly might spend an hour and 45 minutes in that range. And then if we move on to the next step where it exceeds that and we start to have that galvanic couple where just kind of aluminum is corroding, and this includes when we have full wetting of the specimens at above 90% relative humidity, you could see that the aluminum is corroding for a much longer time on the fast ramp, whereas in the slow ramp, the aluminum isn't corroding quite as long, but the steel is corroding a much longer. So the end result is that in the same 4.5 hour test, in the fast ramp, the aluminum corroded for 4 hours, and the steel only corroded for a half hour. Whereas in the slow ramp, the aluminum only corroded for 3 hours, but the steel corroded for almost 2. And they could have vastly different results in the same conditions of this test, just based on the ramp. So as mentioned, JASO decided, because the equipment available didn't really have the ability to do these linear ramps, the idea is let's do it as quickly as possible. That way, we're only talking about a difference of maybe 5 to 10 minutes in that non-galvanic region. And that way they don't have to worry about two different testers or two different tests run at different times performing differently. And as you can see, the areas that we have highlighted are that kind of that key range that we were talking about, where you're going to see that corrosion that covers both the steel and the aluminum. It bypasses that galvanic couple. So while this is a lot faster and and it has that repeatability, it may not be realistic because materials outdoors do see a lot of relative humidity between 50 and 76%. So ultimately, all of this can be traced back to the only limitations that they really had in the first generation of testing is that there wasn't really great equipment available that in salt spray cabinets that could really control that relative humidity. And because of that, they couldn't control transition times. They didn't have the repeatability and reproducibility that they were looking for. And so you'd have to do a lot more testing in order to be sure of how a material is going to perform outdoors. The other thing that they ran into is that, with the exception of 9540P, they all applied salt with fog, and fog took a really long time to apply. And so they needed some faster way to apply the salt so that they had more time to spend in these humid environments. And that's what brings us to kind of the modern corrosion tests. The testers became better equipped to run it. And so now a lot of these tests have replaced fog with what they call spray or shower. These testers can control relative humidity during these ambient phases to reduce repeatability issues. And they can also control the transition times, which allows for better reproducibility between different cabinets. So here's an example of our QFog and how we deliver shower. So we have a shower module in the center that sprays up. And because of the back pressure in the chamber, it uniformly distributes it on the specimens within the chamber. The other thing that this tester can do is control relative humidity, which we'll give a little bit of a diagram on how we do that later. So when we say modern automotive corrosion tests, these are the ones that we're talking about, generally speaking. You'll notice that most of these are automotive OEMs. They're the ones that have really been driving this technology. There's not as many corrosion tests that you'll see like this in, say, the different standards bodies like ASTM and ISO, just because those are kind of more open, and a lot of times it's a metallurgical task group, whereas the automotive manufacturers are the ones that are really pushing this salt delivery and controlled relative humidity. So we talked about the delivery rate of salt. To give you an idea, the difference between 1 hour of fog and 1 hour of shower is that you'll see about 100 times the salt solution delivered in 1 hour of shower. Now, almost no modern test methods actually deliver an hour worth of shower. Most of them will deliver between 10 to 20 minutes per day of shower. And it's going to use up, the same amount of solution as you might see from running 2 weeks of a fog test cycle, because it's applying it very quickly. Also, a lot of them are still using corrosion coupons, as mentioned in GM 9540P, because it's another check to make sure that a tester has not malfunctioned. One of the problems that they run into, particularly with GMW 14872, which is the newer version of 9540P, is that the solution that they use can clog the shower nozzles. And so these corrosion coupons can be used to identify if you have any problems with your shower delivery during the test. And to give you an idea of what we're looking at, so this is a diagram of the various positions on a vehicle and durability levels of the material, and that largely determines how long that you're going to be running the test. But in this window, you'll see that we have the two black lines that are outlining these boxes, and that's the general range of mass loss that you're looking for on these coupons per day. So the cycles at the bottom, each cycle is 1 day, and as you can see, if you're running a 90 day cycle, you're looking for about a mass loss of about 13 grams on these coupons. To give you an idea, these coupons are 25 by 50 millimeters, so 1 by 2 inch, and at the start of the test, they're usually about 30 grams. So in 90 days, these coupons will lose almost half their weight. So let's talk about controlling relative humidity. So one thing that you'll run into with a lot of these test methods, because they're speccing out ambient conditions, which when we say that, we usually mean around 23 degrees Celsius and 50% relative humidity. You will need an air preconditioner in order to meet those conditions. Lots of testers have the ability to control relative humidity, but the way that they do that is by adjusting how much air they're recirculating in the chamber versus how much air they're bringing in from the ambient environment. There is no normal mechanism to remove moisture from the air. So if you have a humid environment that your tester's installed in, you will not be able to meet the ambient conditions. But this air preconditioner, which will remove moisture from the air, replaces that lab air with dry air. And with our tester, you can do it with cool dry or hot dry air. And that's used to kind of control the relative humidity in the chamber, and that gives a much wider range of what can be reached. So the reason it really is necessary. So a lot of times you'll get the question, do I need this? And the answer is you do, because ultimately to run the control loop, you need to have your tester needs to have some idea of what kind of air is coming in, and if it's in an environment where that air is going to change in moisture level day to day and over the course of a day, it's hard to actually control that, particularly if you're ramping. And then the second reason is that if you have a hot, humid lab, you're not going to be able to run a lot of these test methods. So this is an example of our QFog and what test conditions it can meet when running in a lab that is 23 degrees C and 60% relative humidity. So this is common for a well-controlled lab. Sometimes it'll be lower, but during the humid parts of the year, you might get 23 C and 60% relative humidity. Each of these blue dots represents a set point in one of the modern corrosion tests. And as you can see, without the air preconditioner, you can hit most of them, but you can't hit the 23C 50% relative humidity point and the 25C 45% relative humidity point, which I believe are in GMW and Ford. But with the air preconditioner, you can meet those conditions. Now, if you've ever been in a test lab, and again, something to keep in mind is that corrosion testers, because of the nature of them and having salt fog, they're not usually installed in where you have all your expensive lab equipment. They're usually in another room. So it's not uncommon to see conditions of, say, 32 degrees C and 75% relative humidity. In that case, you're not going to be able to really run this tester without an air preconditioner. But instead of having to, say, create an air conditioning system for a warehouse or wherever these testers are being installed, by having an air preconditioner on the front of it, you can still hit all the points from these modern test methods. And as we mentioned before, it's almost impossible to control the ramp of the relative humidity without knowing the humidity of the air coming into the tester. And so here's an example of two testers. The one on the right uses an air preconditioner. As you can see, the blue line that transitions from 100 down to 70, it follows it almost exact. Whereas while the temperature might follow on the left, the relative humidity drops drastically. And so they're really not controlling the ramp, and that's going to affect the amount of time that they have that galvanic corrosion in this test. So these are all things to keep in mind. And so modern corrosion testers have really gotten to the point where they can run these test methods. And some of these modern test methods have very good correlation outdoors. But that's not to say that some of the older methods like salt spray are obsolete. I mean, you wouldn't want to use a salt spray test as a correlation test to develop a new formula, but they're still very good pass-fail tests for quality control or qualification. Wet-dry tests, they're good comparative tests, but they have a high amount of variance from test to test. Combined weathering and corrosion can provide good outdoor corrosion for some materials. Now, something to keep in mind now in say, the automotive industry is a lot of materials have become very durable to the UV portion. And in those cases, sometimes a combined weathering corrosion test method isn't appropriate because it just doubles the length of the test. And first generation cyclic automotive tests were comparative, but they didn't have the repeatability, mostly because the test capabilities weren't there. But modern test methods, if you're really looking for, a correlation test, you want to have a repeatable test that can be run in multiple locations, control of relative humidity, and in many cases, salt spray are going to be better for that. And that brings us to the modern day. So if anybody has any questions, I think we're going to take a few minutes to field them now. And then after a little bit, we'll go to Thermotron for their presentation. So we're going to be handling the questions using the questions feature in GoToWebinar. If there's a question that we think is going to be valuable to everyone, we'll answer it here on the screen. Otherwise, we'll just answer them directly if it's something that's specific to maybe your application.
Okay, Bill, we had a question that came in. What is the best way to increase or decrease mass loss rate for GMW 14872 test? And is it like increasing the spray time or the ramp times between steps?
It's a good question. So for GMW, kind of a lot of it depends on the manufacturer. So for us, the way that we adjust the mass loss is by adjusting the spray on-off time. So the way that the test was originally run is that they would apply the salt spray in an environmental room with, say, like a garden sprayer. And so there is no set collection rate that's necessary in that test method. But what we can do is we can set our tester to on-off time. And so if you're getting low mass loss, you can increase the on time. And if you're getting high mass loss, you can increase the off time. And we've found that that's a pretty good chance of meeting that. We've also found that, with our default settings that we use for our tester, we can set it once, and assuming that you don't get any clogs, there should be no problem over the duration of the test. You should be in range. Now, other manufacturers, you might get a change in uniformity of the salt spray by adjusting the on-off time or adjusting the pump rate that they're using. So I can't speak to that. But for our testers, you would use the on-off time.
Bill, are you required to have an air preconditioner if you're doing ASTM B117?
No, an air preconditioner is unnecessary for B117. It's really only necessary for a test method that uses what we call ambient conditions, where it's no salt fog. Kind of a lot of the dry off test methods that they use are what we would consider, an ambient condition, because a lot of those are 23 degrees C and 50%, where most corrosion stops. In fog tests, particularly B117, the preconditioner is not used.
One more here. Are non-automotive industries looking at cyclic tests to replace B117?
Yeah, there is some investigation on that. I know that AMA is still looking into other tests, and just because their qualification test doesn't use a modern test, it uses that Corrosion test. That doesn't mean that when people are developing new coatings, they're not using modifications of these test methods. I believe GMW 14872 is pretty widely used even outside of automotive.
Okay. Thanks, everybody, for your questions. You can continue to send them as you think of them, and we'll answer them in the chat and the question box. But I want to throw it now over to Chris Schulten at Thermotron. So, Chris, I'm going to throw this over to you now and give you control of the webinar.
Good morning, everyone. I am not Chris Schulten. I am Sarah Brown, actually, the marketing designer here at Thermotron. And welcome to Basics of Environmental Testing. Our presenter is Chris Schulten, and he's our regional sales manager here at Thermotron. He's been here for more than 20 years, has his Bachelor of Science degree in Mechanical Engineering, and has worked as a design and applications engineer before becoming the regional sales manager. I hope you enjoy the presentation, and I'll let Chris take over.
All right, thank you, Sarah. So what I'm going to be doing today is just giving you a real broad overview of environmental testing. We'll kind of dive into a few subjects a little bit deeper. So for those of you that have not heard of Thermotron, we're a manufacturer of test equipment, and I could kind of describe it as we make everything except for the salt spray stuff that we talked about this morning. So it's a wide variety of temperature and humidity chambers, vibration, altitude, dust, some rain, so almost any other environment other than the salt spray. We're located in Holland, Michigan. We've got a couple of different facilities. We just bought a third, and then we also have a facility in England that serves as our European headquarters. So the few things we're going to talk about today is why we test, what are the reasons different companies test, and you'll see there's quite a wide variety just depending on the industry and then the size of the company. We'll talk a little bit about an overview of different type of environments, which I'll refer to as stresses, because when you're testing, those environments become a stress on your product. And then we'll finish up with some considerations when you're looking at equipment. So first of all, why do we test? One of the big reasons is simple simulation. And we'll dive into that in a little bit. Product reliability is a big reason. There are OEM test requirements that your company might have to meet in order to sell to one of these larger companies like a Boeing or a Ford or the military. And then the final one we will touch on is ESS or burn-in. So first of all, simulation testing. So this is simply replicating the environment that your device will be operating in. So to summarize it, it would just be, hey, is this product that we just made, will it work in the final environment that it's going to be used in, or will it work in the field? And these environments could be temperature, different humidity levels, could be operated at a high altitude or subjected to some vibration. So as an example, the automotive industry, their typical test range that they'll work with is plus 85, which would be, you know, if you've ever gotten into an automobile in Arizona after it's been sitting in the sun all day, gets very hot, so maybe as high as 85 degrees C or 185 degrees F. And then if you've ever spent any time in Minnesota in the winter, you know temperatures can get very cold down to a minus 40. So the automotive industry has looked at their wide range of temperatures their vehicles will be exposed to, and they've set that as kind of a standard temperature range. And then a lot of times, products will be exposed to multiple environments all at the same time. And I know in the news lately, one of the big ones has been the huge recall of airbag inflators. And I think it's up to almost 50 million cars that are recalled now. And that root cause of failure was that chemical in there was exposed to high humidity levels and repeated temperature swings over time. So a combination of two different types of environments or stresses. So the takeaway there is it's really important when you're making a product to have a real good understanding of all the different types of environments or stresses that'll be exposed to. And I can tell you here at Thermotron, a lot of the testing that we do on our control systems or when we come out with a new product is this type of simulation testing. So where will the product be located? What type of stresses will it see? Or during transportation, what kind of vibration levels is it going to see? So one of the other types we'll see is trying to predict the reliability of a certain product. Product reliability is quantified with something called mean time between failure, or MTBF. So reliability engineers will use resources like the Mill Handbook 217. There's a lot of softwares out there that you can plug in different parameters and it'll give you a mean time between failure. And there's just a ton of formulas and a lot of pretty complex math that gets into reliability engineering and what will stresses do to the end product. To give you a real simple example, there's something called the 10C half-life rule, and it simply is if you operate specifically electronics at an elevated temperature, and so if you have electronics that are meant to operate at ambient temperatures, you raise that temperature 10 degrees C, the life of those electronics or components will be cut in half. So you can kind of flip that around and say, okay, if we do a test at 80 degrees C for 30 days or 60 days, here's the predicted life that we can expect out of it or calculate based on that test. So reliability engineering, it's obviously complicated. That's just a real basic example. And then kind of under the category of reliability testing, there's something called halt testing that's really used by a majority of large tech companies these days. And it's unique in the sense that it isn't a test to pass, but really a test method to try and force failures in a product. So the equipment itself, it's vibration, it's extreme temperature changes, and the vibration resembles a bunch of jackhammers on the bottom of a test plate, and it subjects that product to really high vibration levels, something it would not see in the field, but trying to stress the product to an over stress situation, trying to find the weakest points of the product. I'm not going to dive into that real deep. If halt testing is something maybe you've heard about or want to find out more, just do an internet search for Thermotron Halt Testing Handbook, and you can download a pretty comprehensive guide on what that's all about. So one of the other big reasons people test that we heard a lot about earlier from QLab is OEM test requirements. So these are requirements that have been put into place that OEMs, like an automobile manufacturer, an airplane manufacturer, I know John Deere is a big one, that they have mandated that if you're a supplier to our company, you need to pass these certain tests. So they've kind of done all of that reliability engineering work and created a big test spec. And there's different specifications depending on the type of component that you have to manufacture. And then the military has their own specifications, and they're kind of unique in the sense that they're all publicly available, where a lot of these other specifications are only available if you're a supplier or if you purchase it from one of these test organizations that I have listed there. So IEC is a common one, SAE, ASTM that we've talked about this morning, UL, places like that. One of the industries I got deeply involved with is the solar module industry. And they were pretty unique because to get a return on your investment of buying solar modules, they would offer a 25-year warranty. So in order to get the confidence of that, they had some really harsh, pretty tough tests that would involve just thousands of thermal cycles, thousands of hours of high temperature, high humidity, and then some obscure things like hail gun testing, all to help ensure that those products would last that long. And generally, in contrast to the halt testing I just talked about, the hope when you're a manufacturer is that you can pass these tests that you're required to. So it's kind of a test to pass mentality. And just for fun, to look at all of the different types of environments out there, and some of the weird ones. Here's a listing from Mill Standard 810, which is it's an 800-page specification that's been developed for manufacturers of military electronics, rugged computers, and perhaps you've even seen consumer electronics like cell phones or rugged laptops that claim they have been tested to Mill Standard 810. So there's just one example. So the type of testing that we've talked about so far is generally done in the design phase or R&D. There's another type of testing that we get involved in called burn-in, or ESS, which stands for Environmental Stress Screening. So this is normally done on production products that are being produced and shipped out to customers. So this graphic here is what's called a bathtub curve by reliability engineers, and determines the failure rate of a population of products. So many products have a statistically higher failure rate during the first part of life, which we call infant mortality, and are obviously failures you don't want your customer to experience. And then these failures are generally due to errors in material or assembly procedures during manufacturing. So just to explain what this is. So this would be a graphing of those infant mortality failures, or right out of the box failures. And this might occur over a week or two, and then tail off over time. This yellow graph is wear out failures, which would be, you know, in the case of a laptop computer, you might expect this stuff to happen after 7, 8, 9 years as hard drives wear out. And then in the green here is just kind of a constant failure sampling. Maybe one fails out of a sample of 1 million. Maybe you get 5 or 10 per week that would fail. So this bathtub curve is kind of a combination of all these. So the idea with burn-in or ESS is to weed out these infant mortalities. So what burn-in is simply operating electronic products, big batches of them, at an elevated temperature, kind of getting back to that 10C half-life rule, to try and weed those out or have them fail before you ship them out to the field. And then ESS is similar in that, except for it uses thermal cycling, perhaps vibration, so a more stressful burn-in, if you will, again, to try and find those failures in your factory. And then there's another method, even more stressful, called HASS, or Highly Accelerated Stress Screening, that's related back to that HALT that we talked about, using the same high-level vibration and ultra-fast ramp rates to weed out failures. So again, ESS gets to be kind of a complicated topic. If you'd like more information, just Google Thermotron ESS Handbook, and you can download a free guide on that. So there's kind of some of the reasons why people test, and I'm going to spend a little bit of time just going through different environmental stresses. And the most common ones we see here are temperature, humidity, vibration, and altitude. So first up is temperature. And what you'll see with all of these specs, and you saw the same thing earlier, is everything is in degrees Celsius. I'm finally used to it after working here for 20 years. So all of these are in degrees C. So a common test range for the telecom industry, for instance, plus 55 to minus 5, and that's based on where those things are located. Like we talked about, automotive and solar, plus 85 to minus 40. The military is generally plus 71 to minus 65. And mechanically cooled environmental equipment will have a range of up to 180 degrees C down to minus 70. So those are kind of limits of technology, the limits of materials. And then occasionally we get requirements for the downhole oil and gas drilling industry that'll be very hot, so we'll manufacture equipment with special materials to accommodate that. And then also with the space and satellite industry, we'll use some special technology, liquid nitrogen, to get down below that minus 70. But these are typical ranges that we'll see. So just a little overview on how mechanical cooling takes place. And this is a refrigerator, just to give you something that you're used to seeing to relate to. So on a refrigerator and an environmental chamber, you'll have a compressor, and it's going to pump a refrigerant through a heat exchanger. And this heat exchanger is on the outside of the workspace, or in the case of a refrigerator, on the outside of the cold space. And as it passes through this heat exchanger, that refrigerant condenses, it's called a condenser, and gives that heat off and cools it down. And as that cools down, it'll turn into a liquid, passes through an expansion valve, which causes that liquid to expand. And as it expands inside of the workspace or inside of the refrigerator, it absorbs all of that heat in there and causes that space to cool down. And then that refrigerant is brought back into the compressor through suction and then is recirculated around again. So this is the exact same concept you would have with a home air conditioning unit. And the basic concept with all of these is you're simply taking the heat and moving it from one place to another. And perhaps you've even heard of the first law of thermodynamics that I learned about in school, that you can't create or destroy energy. You can just move it or change its phase. And that's really what's going on here with a mechanically cooled environmental chamber, or in this case, a refrigerator. So down here in the left corner is a graphic of what I just showed you, a simple one compressor system, and this is what we call a single stage refrigeration system. And with the correct refrigerant, this will get you down to about -40. And I told you earlier, with environmental chambers, we go down to -70. So that uses something called a cascade refrigeration system. And that'll have 2 compressors, a heat exchanger in the chamber, one outside like we talked about earlier, that'll get rid of the heat, and then there's something called a cascade heat exchanger that allows those 2 systems to work together to get down to those ultra cold temperatures. So I mentioned that single stage at its lowest is capable of getting down to -40. And here's a chamber that I ran out in our lab. Here in blue, you see a single stage unit. Here in red, you see a cascade unit. And the reason I'm showing this to you is if you have a test requirement where you need to ramp down to -40 quickly, or perhaps you've got a product that gives off a lot of heat down at -40, usually the application would call for a cascade, because this will continue ramping pretty quickly right down to -40, where the single stage kind of levels out, and may not be the best use of that technology because you're right at the edge of its limit. So here's a typical chamber design. So where you've got the airflow circulating around here is the workspace. So this is where your product would be located. These blue rectangles here represent the evaporator coil, or where the refrigerant goes through, and then also some heaters. And those heaters are very similar to what you would see in your toaster oven at home, so they get glowing red hot. So when we're heating up, those heaters turn on. When we're cooling, the refrigerant flows through the coils. And then this represents a fan up here, so it's circulating air over the heat exchanger, over your product. So if you were to open up the door of a environmental chamber, you'd see air coming out of the top here, and then circulates around, and then back in through the bottom. And then up top here is how they're controlled. There'll be sensors there to sense what that air temperature is coming out of the chamber. So most of the specifications that we discussed earlier have a requirement for temperature ramp rates. So as an example, this comes out of an IEC specification for solar panels, and this specifies 100 degrees C per hour max, which calculates into about a 1.6 degrees C per minute average. So one of the biggest variables we get with environmental chambers is exactly that. How fast do you need to go from one temperature to another? And even though the technology is the same as a refrigerator, the horsepower is what changes both the size of the chamber and certainly the cost of the chamber. So if you need to go 1 degree C per minute, it might mean a 1 horsepower compressor. If you need to go 20 degrees C per minute, you might be dealing with 30 or 40 horsepower compressors, which drive size, facilities costs, and certainly chamber costs. So just a feel for what's possible with change rates. Another pretty important consideration is when looking at those specifications, is it specified as an average change rate or a linear ramp? And this was something, again, we even saw back in the salt spray. Are you trying to change at a fastest possible ramp rate, or is it a linear change? And so here's an example, the same chamber. I programmed it in 85 down to -65 and just let it go as quickly as possible. So you'll see it's faster up top where the refrigeration has more capacity, kind of levels out in the middle, and then slows down as it reaches its coldest temperature it's possible above. So this ramp took about 33 minutes, which is about 4.2 C per minute. If we program in a linear change, we're actually slowing the system down so that you get an exact 4 degrees C per minute. The danger you run into there is you're not taking advantage of that high capacity, and down at the bottom end, you might see it tail off, or it won't maintain that 4 degrees C per minute, which would result in a need for a larger horsepower system. So the reason I mention it is it's something we ask when somebody's asking for equipment. Is it an average change rate or a linear change rate? And when we understand that, then we can specify the right compressor size. So here's a graph of typical response in an environmental chamber, just a test I did out in our lab. So ran the chamber from ambient up to 100 degrees C, represented by the red line there. So there's a thermocouple in the chamber, graphs out that temperature. In the green is a thermocouple I placed on a product, and it was just a small valve, weighs a few pounds. And it kind of graphs out what you would expect to see. It's not going to ramp in temperature as fast as what the air does. And then just depending on how heavy it is, it'll lag behind that air temperature and eventually get to set point. And the same thing when we cool down. You see the temperature go pretty fast when it's cooling, and then the product will lag behind. So this took about 40 minutes to heat up, about 30 minutes to heat down. One of the methods you can use to speed that up is something we call product temperature control. So in this example, I ran the exact same test temperatures, but based off of the product temperature. So you'll see the air temperature, instead of just going up to 100 and allowing the product to get there over time, what we did is programmed in an overshoot. The air temperature goes up to 110 and forces the product to get there much quicker. And then as it approaches 100 degrees C, or the set point here, the air temperature will come down and they both converge on that. The benefit, it takes about 50% less time to get the product to temperature compared to just using a conventional control method. So that's an overview of temperature. Next thing we'll talk about briefly is humidity. So it's just humidity, like we talked about earlier, can obviously cause corrosion in metals, even just plain humidity, and it can also affect a lot of different polymers and, of course, electronics. And I read something the other day from a university study that estimated about 20% of all electronic failures are due to humidity. So condensation on a circuit board can cause current leakage, or if there's enough condensation, even a short or shorting out. In an environmental chamber, humidity is most often produced by a vapor generator. So we will boil water in a device that looks like this. So it has a heater submerged in water, and then that steam is produced and it's piped into the environmental chamber. And then when we want to reduce the humidity level, there's something inside called a dehumidify coil. We'll send a little bit of refrigerant through it, get the temperature of it just below freezing, and that'll condense out humidity. Same concept. If you've ever had a cold beverage on a hot, humid day, you'll get condensation on that surface because condensing that humidity out. That temperature is below what the dew point of that condition is. So we condense out humidity in the same way. The way we measure humidity in an environmental chamber is using a solid state capacitive sensor. So we read it with a sensor that feeds back to the controller, and then if the humidity level is too low, we turn on the vapor generator. If it's too high, we turn on the dehumidification system. And this graphic shows a typical humidity range that's possible in an environmental chamber. So the range will be about 10% all the way up to 90%. And then as far as temperature range, we're generally 10, 12 degrees in between 100°C and 0°C, which are boiling point of water and the freezing temperature. Anything above 100°C really requires pressure, like a pressure cooker. And then anything below freezing, you simply can't produce humidity because it turns into ice right away. So what is relative humidity? With all of these test specs, everything is specified in relative humidity. So as an illustration, here's 2 cups of water, which represent a cold air and a warm air. And they both have the exact same amount of water in it, or the exact same amount of humidity. So this would represent air which is 50% saturated. So in this example, 6 ounces of water in a 12-ounce cup. As you warm air, it has a much higher capacity to hold moisture. So in this example, the air is a little warmer. You have the exact same amount of water or absolute humidity, but since it can hold so much more, now it's only 25% full, or something expressed as 25% humidity. So in practical terms, with an environmental chamber, if we have a 1 cubic meter chamber, it can hold about a ½ ounce of water. So if it had a ½ ounce of water in it, it would be 100% humidity. If we raise the temperature just 10 degrees C, so from 20 degrees C to 30 degrees C, it can hold double the water. So just by raising the temperature, it would go from 100% humidity to 50% humidity just by changing that air temperature. A couple of other points I want to make when it comes to humidity testing in chamber. When you're testing a product that gives off a lot of heat, special considerations are required. It's very difficult to test humidity conditions with a lot of live load. If you need to control both temperature and humidity at the same time, that would be normally done in a steady state condition. If you see test specifications that require the changing of humidity or the changing of temperature and humidity at the same time, the key to doing that successfully is doing it very slowly. Water purity, very critical with humidity chambers. You'll see in the manual, there's stickers all over the chamber that you have to have a water that meets a certain purity level. And then just understand the difference between holding a precise humidity condition like 40 degrees C, 50%, requires a humidity chamber with precise control. There's also test specifications which will simply say you need to run 50 degrees C less than 20% humidity. So it's just calling for a hot, dry condition, but doesn't require you to hold to a precise humidity level. And we can do those without a humidity chamber just by injecting a dry gas. So a couple of the final environmental stresses I wanted to touch on are vibration and altitude. So the systems you see shown here are called electrodynamic shakers. So you've got something that looks like a big steel subwoofer, essentially, and it's the same type of technology. You have a control system that would be very similar to almost what you would see with an audio system. It's very similar to an MP3 player in that it can create signals very similar to what a music would be, and then also an amplifier just like on an audio system. So there's a lot of different vibration specs that mimic certain vibration profiles. So for example, our equipment typically goes into a lab environment where there's not a lot of vibration, but it's certainly shipped all over the world. So with our products, we're not concerned so much about end-use vibration as we are transportation vibration. And there's specifications that you can look up that do exactly that. They give you that profile that mimics transportation. And then the automotive industries, the aerospace industries have their own vibration specs that are meant to mimic the vibrations that come from takeoff and landing, or the vibrations from an engine running. And then up in the top here, you'll see vibration systems coupled with an environmental chamber. So those were sold to customers doing both vibration and temperature and humidity at the same time. And then one of the other ones I mentioned is altitude, which is a chamber that looks a lot like this, and we'll use a vacuum pump to draw the air out of there to simulate altitude levels up to 100,000 feet. So here's a test that we did in the lab, and I want to point out a few things here. There's these holes in the side of the chamber with a lot of wires going in and out, and most testing of products that are electronic or products that move are always done live. So you'll see the gauges are active here, the lights are on, and the reason for that is so many of the failures that we find in the lab and also our customers find, or your customers find, only occur while they're being stressed. So if you're just simply placing a product in a chamber and not operating it during the test, you miss a lot of those intermittent failures or failures that only occur while they're being stressed. Or your reliability folks might refer to those as warranty returns that are no problem found. So we plug it in when it came back from the customer as a warranty, we plug it in and it works just fine. Perhaps if you stress it in an environment, you can then reproduce that failure. And I'll tell you, on an environmental chamber, there's a pretty powerful controller, and a lot of the advances that have happened over the last decade have to do with this exact same thing. Monitoring products, supplying voltage to it, turning products on and off, and then detecting those real short duration intermittent failures. So just a few other things to consider with environmental testing. How large is the product compared to what the test specification is? When you place something in a temperature humidity chamber, we generally recommend that it's only 1/2 to 1/3 full, so you have good airflow around it. No different than if you're cooking something at home. You can't stuff an oven completely full of food, or it just won't properly cook. So really important that we get good airflow around it so the whole product changes at kind of a uniform temperature. One of the other big considerations we get, especially in automotive and aerospace, is are there any fluids involved in your testing? Are you pumping gasoline through that fuel pump, or is there a flammable cooling fluid through the aerospace electronics? Because those require special considerations, and will end up making the interior workspace to C1, D1 standards. And then some of the facilities items, just looking at exterior limitations. Can you move it into place down the hallways? Will it fit into the lab that you're considering? Here's just a quick photo of somebody that couldn't physically get the chamber into their lab down the hallway. So we ended up building some special packaging for it, and they lifted it up through the window. And then some of the other questions our field salespeople ask, things for you to consider in addition to the product is it giving off a lot of heat? Do we have to accommodate for that heat when we're sizing our refrigeration system? If yes, how many watts are given off? When is it given off? Only at high temps, only at low temps, during transition? And then the one I cautioned you on earlier, is that given off during humidity testing? Just a few other facilities items. What kind of power do you have available? Generally, these require three-phase industrial power. Do you have cooling water available? And when I showed you the refrigeration earlier, that heat has to be given off somewhere. So it's either in your lab that is going to be taken care of by the HVAC system, or a lot of the larger systems will require cooling water. Then other things like our other utilities available, like LN2 or compressed dry air. So that gives you just a big overview of different types of testing, why people test, the different stresses, and then some of the facilities items. So we will, like we did earlier, open it up for a couple of minutes if there's any questions at all.
Hey, Chris, we had one question over here. Is there a way to prevent scaling on the heaters used in the humidifier? Was one question.
Yeah, that's a great question. So that goes back to generating humidity, and the way we do that is there's a heater in a tank of water. It boils that water, the water vapor goes into the chamber, and what gets left behind, the scaling that was asked about, is the impurities in the water. So the water leaves, all the minerals stay behind, and eventually it'll build up and scale on the humidity heater, and that's a reason those humidity heaters can fail. So the way to prevent that is to use the correct purity of water so that you don't have all those minerals behind, and also to flush those out once in a while, just like you do with your hot water heater at home to get rid of those minerals.
Another question that came in is dehumidification via moisture condensing the same thing as dry air purge? If not, what is the difference?
Could you repeat that?
Sure. Is dehumidification via moisture condensing the same thing as dry air purge? If not, what is the difference?
Oh, sure. Yeah, so there's different ways to get rid of humidity out of an enclosed space like a chamber. One is with dehumidification. So we would condense the water out, and then that would drain out of the chamber, causing that closed workspace to be dry. One of the other methods of drying out a chamber is to inject it with a dry gas. And that can either be compressed dry air that you might already have in a facility, or a gas like gaseous nitrogen. Or those two can simply be used together to speed up that drying time.
Thank you very much. Can an ultrasonic humidifier be used instead of a boiler?
Yeah, certainly. And so we use a boiler in environmental chambers because it really serves a wide range of humidity conditions, both on the low end and on the high end. When we get into certain applications like high humidity, high temperature with a lot of live load, we will use an atomizer system either on its own or in conjunction with a conventional vapor generator.
And lastly, why is humidity control disabled for altitude control?
Yeah, another good question. So when you're trying to do a combination of altitude and humidity, Essentially, you're trying to suck all the air out of the chamber to simulate altitude. So trying to add in water and along with the air and trying to pull all that out at the same time becomes difficult. And there's the added problem of vacuum pumps really aren't made to deal with water. So when you're doing altitude testing, generally we lock out the humidity levels. And there are some systems we've built where it does combine those, but they get expensive mostly because you have to have a vacuum pump that's really meant to deal with water and humidity.
Thank you very much. I think that's it for the questions for now.
Okay, thanks everybody. Thanks, Sarah, and great presentation. A couple of people have asked during the question time here if we'll be sharing the PowerPoints and the presentations. Yes, we're recording this webinar, and we will email the links to everyone in the next couple of days to the PowerPoints and the recording, so you can watch this. Watch us at home and enjoy it again in the future. But again, thank you everybody for attending today. I really appreciate it. Thank you to everyone at Thermotron for your help with this webinar. Have a great rest of the week, and see you at a future webinar. Thanks a lot.